What we're going to do today is we are going to talk about why that is the case. So in this particular justification of the activity series and reactivity of metals with water, we use the activity series to explain why some metals react with water or acid, but last year when we told you about it, it was only based on the fact, like, here, use this chart. Today I'm going to teach you how to calculate that so that you always know without having to have the chart, because you will not get the chart on the AP exam. Now, example number 1 says metals can displace H2 from an acid, lie under the standard hydrogen electron cell potential half reaction, and metals that cannot displace lie above. So, the example that you're given here, and I'm going to make a very, very large point that what is written right here is subtly different than what's in your notes. Okay, do you see that? I'm going to try to explain why, so please hang on and pay attention. If I look at the original equation, which is what everything is based off of, in this case, potassium is a 0, and potassium becomes a +1. Because it becomes a +1, it has lost electrons, correct? Yeah. So that makes it an oxidation. So we would say potassium oxidizes, not co-oxidizes. Okay? But hydrogen is a +1 times 2, and it eventually becomes 0. So the hydrogen, which is a +1, reduces. Now, in Appendix E in your textbook, and in every reduction potential list, they are always written as reduction reactions no matter what they are doing in the actual equation. You can't have a redox reaction without having an oxidation. But when you go to the textbook and you look at Appendix E, you see them all written as reductions no matter what. So what I've done today is I've written them as reductions as they appear in your textbook, but I'm going to always go through and identify which one oxidizes and reduces based on the chemical equation that we're starting with. So in this particular case, because the potassium oxidizes, because of the data that says that potassium oxidizes, I'm still going to write the potassium reduction half reaction. Okay? Now the hydrogen one was the one that reduced anyway, so I didn't have to change it. But the deal is that because I know now which one is the oxidation and which one is the reduction, I can simply put it in the cell potential calculation, or formula rather, and get a value, in this case, of positive 2.92, telling me that the reaction is thermodynamically favored. So Nina, when you asked before, like, why are they written the way that they are in the textbook, this is why. Does that make more sense?
Can you say before I get about the, like, when it goes to positive 2.92?
Okay. So in the textbook, the value for the half reaction cell potential, or reduction potential rather, of potassium is negative 2.92. And in the textbook, in Appendix E, the half reaction cell, reduction potential for hydrogen is 0. But because hydrogen is being reduced and potassium is being oxidized, when I plug these values into this formula here, I take the reduction, which is 0, minus the oxidation, which in this case is negative 2.92, and I get a positive 2.92 as my total cell potential. And as a result of that, that tells me that this reaction is thermodynamically favored. That tells me that on my activity series of metals, potassium is somewhere above hydrogen, so potassium can replace it.
So, in the textbook, it gives you the reduction?
It always gives you the reduction.
So you don't need to change the sign or anything
That was
when
my
the
question.
oxidation?
And that's another question. The question is, do you have to change the sign? The answer is no, because that's the value of the reduction potential, even though it's an oxidation.
Okay.
here's another example. In this case, copper is written as a 0, it becomes a +2. So because copper is written as a 0 and it becomes a +2 in terms of its oxidative state, it has lost electrons, so it is oxidizing. And hydrogen started as a +1 and became a 0, so that means that it reduced. Okay, now, in this case here, I grabbed the half reactions as they appeared out of the textbook. So when I grabbed the electron cell potential, or the reduction potential for copper, it's a +3,4. The reduction, or the reduction potential for hydrogen is still 0. So when I plug those values into the cell potential formula, I get the reduction, which is 0, minus the oxidation, which is 0.34, and I get a value of a negative 0.34. So this reaction is not thermodynamically favored. So again, if potassium is up here and hydrogen is down here, potassium can replace hydrogen. But if copper is below hydrogen, copper cannot replace hydrogen because it's not thermodynamically favored.
So, like, if we were, like, on a test, if we write the equations just in the reduction form, but identify which one's oxidizing and which one's reducing, is that fine, or do we always have to switch them?
See, I didn't, oh, if you're asking if you wrote the copper one as an actual oxidation, like if you're actually, are you asking if you wrote it like this?
That's how it's written on our thing, but I'm saying, like, can we just write it like that? Just
Yes, and that's what I'm getting at. Like, I thought about it a lot last night, and I changed it on my notes so that, because this is what comes out of, the textbook,
Yeah.
and since that's what you guys are gonna see a lot, I decided to make it as uniform as possible. Does that make sense?
Yeah,
Okay,
and just, you wouldn't, like, it wouldn't matter on a test as long as we identify which one's which.
correct. Now, metals can displace H2 from water lie below the half reaction for the reduction of water. Metals that cannot displace H2 lie above. So here again is the reaction that supports this. So magnesium starts as a 0, becomes a +2. So because magnesium seems to have lost electrons, it's the oxidizing one. And hydrogen in this case is a +1, and there's like a bunch of them, but it becomes a 0, so the hydrogen is the reducer. And again, I pulled this equation and this equation directly out of the textbook Appendix E, and by doing that, I just grabbed the values that are associated with it. But because I just went through the effort to identify which one was oxidized and reduced, I just left them alone. So in this case, to calculate the cell potential to determine if this reaction is thermodynamically favored or not, I took the reduction minus the oxidation. So the 0.83 minus the negative 2.37, and I got a positive 1.54 volts. So that tells me that this reaction will occur. It is thermodynamically favored. So magnesium, in this case, metals can displace hydrogen from water, lie below the half reaction for the reduction of water. So these are below the water half reaction on the Appendix E. Whereas, so what we're talking about here is that metals that can displace H2 from water. So we have water, and we're looking for a metal that can remove the H2, okay? Those lie below the half reaction for the reduction of water on the half reaction reduction table. Metals that cannot displace lie above, and and let me try to show you, so hang on a second. In this case, I have tin, which is a 0, becoming a +2. So tin lost electrons, so it oxidizes, and hydrogen again, +1 to 0, reduces. So I grabbed these values directly out of the textbook, and I identified that tin oxidized, and I identified that the hydrogen reduced. I grabbed the cell potential for hydrogen to be 0.183, or for water rather to be 0.83, and for the tin to be negative 0.14. Yes, Megan?
Can you explain the line below or above the half reaction for the reduction thing?
Yeah. Give me a second. Let me finish this one. So in this case, we have the oxidizing, we have the reducing minus the oxidizing, so the negative 0.83 volts minus the negative 0.14 volts gives me a negative 0.69 volts, and because the cell potential is negative, this is not thermodynamically favored. Now, to go back,
So does it form SNOH?
well, because it's aqueous, it doesn't actually form SNOH, it forms tin ion and hydroxide ion.
Okay, so it doesn't like,
Remember, we're putting solid, so we're basically asking, sort of in a way,
does the hydroxide will dissolve, right?
well, the hydroxide in water is, we can rewrite it as HOH, right? But what we're really asking here is, can we remove essentially 2 hydrogens from water with tin?
Okay.
And the answer in this case is no, based on the math. Do you follow that? Okay. Now this is the one that you're really familiar with. This is the one that says any metal lower on the list can reduce a metal higher on the list and displace that metal from solution. So zinc replaces silver in silver nitrate. So here's your formula for the chemical equation. So we have a 0 and a +2 and a +1 and a 0. So the zinc lost the 2 electrons, so that means it's oxidizing. And the silver gained electrons, so that was meaning it's reducing. So in this case, when you take the reduction potential, the half cell reduction potential for silver minus the oxidizing half cell reduction potential for zinc, we get a positive 1.56, and as a result of that, this equation is thermodynamically favored. So zinc can replace silver. Does that make sense? Nickel, however, will not replace iron in iron chloride. So we have a 0 and a +2. So that tells me that nickel has lost electrons, so it's oxidizing. And iron is +2, and it becomes a 0, so that is reducing. And when I grab those values out of the textbook, Appendix E, I get a negative 0.28 for my oxidizer and my negative 0.44 for my reducer. So I take reducer minus oxidizer, and I get a negative 0.16. So this will not happen. So in this case, as this half reaction is written, nickel can't replace the iron. So nickel won't become an ion in this battery system. Yes?
Can you also do it by looking at which one is smaller? Like a smaller value? Or do you have to go?
It depends. I mean, if the question says, will this reaction occur or not, I think that a person could do this in their head. However, if the question says, what is the cell potential,
Oh, yeah.
you're going to want to show work. I don't think you want to just do it in your head.
Yeah, because usually like when it's like a smaller number, it's lowercase. Because like here, like at these smaller.
Right, but what I'm saying is like if, I'm sure that the set of questions is probably not going to just simply be will it replace. It'll be a series of questions that might be one of them. Okay? So to try this, okay? In this case, we are going to write the half reactions from this full reaction. So the first half reaction that I have, first of all, I'm going to say it's that the lead becomes a +2. I can see that by just what's written here. So that tells me that the lead is going to be oxidizing. And in this case, we're looking at hydrogen. Hydrogen's a +1, becomes a 0. The hydrogen is reducing. So I'm going to write the reactions as they're written in the textbook. So I'm going to say that lead And when I grab that value of the textbook, I get a 0.126 volts. And for the water, I'm going to write and that's a value of negative 0.83 volts. So the reason why I wrote this reaction here with the two waters, even though it's not in this balanced chemical equation, is because we did have to balance this particular reaction, the half reaction as it is. And again, I just pulled it directly out of the textbook or the appendix. So I just kind of went with what was given to me. Now, in this case, I'm asked to calculate the reduction potential, and that's going to be the reduction, standard reduction, minus the standard oxidation. So I'm going to take my negative 0.83 minus my negative 0.126, and that's going to give me my cell potential to be negative 0.704 volts. So this is a not thermodynamically favored reaction. Okay. Now with the next one, chromium starts at a 0, becomes a +3. So that tells me that chromium is the oxidizer. Tin starts at a +2, goes to a 0. So that tells me tin is being reduced. So when I go to grab those values out of the textbook, I have chromium +3 plus 3 electrons reacts to form chromium. And according to the textbook values, the half reduction potential is negative 0.74 volts. For tin, the half reduction potential is negative 0.136 volts. So when I go to plug this into my formula, I'm going to take the negative 0.136 volts minus the negative 0.74 volts, and I'm going to get a cell potential for this particular reaction to be positive 0.604 volts. So this is thermodynamically favored. Now, we've got some time left, so I'm going to push forward a bit. Doesn't necessarily change your homework assignment, but I just want to keep going. The Faraday constant is a value that you're not going to have to memorize because it is given to you on the AP exam, but you should be aware that the total charge of 1 mole of electrons is a value that we know. It's a constant. We call it the Faraday constant. The Faraday constant essentially comes from 6.02 times 10 to the 23rd electrons per mole times the charge on one actual electron. And the value for the charge on one actual electron is 1.602 times 10 to the minus 19 coulombs per electron, which gives us a value for the Faraday constant to be 96,500 coulombs per mole. And remember, the coulomb is joules per volt. Do you have to memorize this value? No. Do you need to be able to use it? Yes. So we're going to go through some derivation stuff. So it's good, clean family fun. And then there's a chart that comes with this, which is also something that's fun. So here we go. The signs of the cell potential and the change in free energy are opposite of each other when a reaction is thermodynamically favored. and are proportional to each other. So what I'm saying is that if I have a cell potential that is positive and I have a change in free energy that is negative, that means that the reaction is thermodynamically favored. And separately, we learned that already. I'm just kind of tying that together. So what this is trying to get at is the change in free energy is proportional to the cell potential. Now, we talked about work earlier this last unit, and electrical work is the product of the charge and the voltage of the cell. That is the ability of the cell to push electrons. So electrical work is equal to the charge times the cell potential. And if the total charge is directly related to the number of moles of transferred electrons, we know that the total amount of work is equal to the electrical work times the number of moles times Faraday's constant times the cell potential. N is going to be number of moles of electrons, and that's going to be important later. And since delta G from way earlier in this unit is equal to work max, if you remember that, then that tells me that change in free energy is equal to the negative number of moles times Faraday's constant times the cell potential. Note the difference between the two formulas. One is at standard state and the other is not standard state. Not too bad yet, so we're going to move forward. You might remember this formula, and when we now have this formula, since they're both equal to the change in free energy, I can set them equal to each other, and when I set them equal to each other, I get a value for that says that the standard cell potential is equal to the ideal gas law constant times temperature over number of moles times Faraday constant times the natural log of K. If I manipulate that just a little bit, I get this value here. This 0.0592 is the ideal gas law constant times the temperature divided by Faraday's constant. So it's RT over Faraday's constant. So that value there is just something that I'm going to kind of work through for some of these problems. So if we can measure the standard state or the standard cell potential, we can directly find K, equilibrium constant, or we can find change in free energy at the standard state. And again, remember the standard state conditions are always equal to 1 molar in terms of solutions, and then the Q ratio for the system is equal to 1. Oh, man, we're tying a lot of things together here. So in standard state conditions, the system is not at equilibrium, and it can't be because that means that the system that the reaction is thermodynamically favored. So oh, sorry, my bad. We good now? Don't worry about it. The cell potential and Q in non-standard state conditions, though, is going to come up. Sorry. Non-standard state conditions exist in electrochemical cells when the concentrations of the aqueous solutions don't equal 1 molar. As a matter of fact, most of the solutions that you ever deal with are not 1 molar, so we have to learn how to handle that. So the concentrations of the aqueous solutions continuously change as reactants get used up and products get made. So as a result of that, the voltage changes as the cell operates. Since change in free energy is equal to change in standard free energy plus ideal gas law constant times temperature times natural log of Q, and change in energy is equal to cell potential being proportional, you can substitute the cell potential and the standard state cell potential for standard free energy change and rearrange to get something that we call the Nernst equation. Now, if by chance, and I'm going to give you a hint here, that when we get the Nernst equation, what ends up happening is that we're gonna end up using this portion of it a lot, because that's the derivation that allows us to have standard equal to, or I'm sorry, non-standard state conditions equal to standard state conditions. So a cell that operates in non-standard state conditions, according to Le Chatelier's principle, say they operate until the system reaches equilibrium when Q equals K. So when Q equals K, the system is in equilibrium and there's no further push on the electrons. So the cell potential is equal to 0. If the cell potential is equal to 0, Le Chatelier's principle allows the cell potential to become comparable to the standard cell potential. And any voltaic cell that operates spontaneously, reactants and products are at equilibrium as long as they're producing electricity. So far, so good with that. So we can have changes in cell potential over time. So remember, as concentrations of reactants are going down, concentrations of products are going up, and the potential decreases.
Please excuse this brief.
If Q is less than 1, that tells you that the reaction concentration is high, and that tells you that the cell potential is greater than the standard cell potential. That's telling you that the high number of reactants in the system will allow the forward reaction to take place at a faster rate, which makes the push on the electrons higher than it would be at standard conditions. So at the beginning of a system, when you first start it, the electrons get pushed faster. When Q is equal to 1, the concentrations of the reactants and products are equal, and the cell potential and the standard state cell potential are also equal. So as a result of that, the push is the same. If Q is greater than 1, that means product concentration is high, the cell potential is less than the standard cell potential, and because we have high number of products in the system, it allows the forward reaction to take place, but at a slower rate, and it makes the push of electrons lower than it would be at standard state conditions. If Q is equal to K, at equilibrium, nothing happens. So the cell potential gives you a dead battery because it's at 0. So the reaction is at equilibrium, and there's no forward or reverse reactions occurring at a different rate, so they're equal, and there's no more push on electrons. So that gives us this fun little chart. This fun little chart allows you to see the interrelationship between change in free energy, cell potential, and equilibrium. So what the chart is telling you is that if the cell potential is greater than 0, free energy change is got to be less than 0, and K is going to be greater than 1. That means the reaction is favored, and the reaction is going to occur. If the cell potential is equal to 0, free energy change is equal to 0, K is equal to 1, we are at equilibrium, and we have nothing going on. If the cell potential is less than 0, the change in free energy is greater than 0, K will be greater than 1, we have a not favored reaction. And what this chart is designed to do is it's designed to show you the different ways to calculate or get from cell potential to, for example, free energy, or cell potential to get to K, but it's been rearranged for you. Today, so your homework is the last set of homework from before. We will finish this up on Monday.
There's nothing else.
I don't think I'm going to get any